We talked about the inception this morning. We talked about some of the evolutionary developments as things got refined and extended. And so we are sitting here in 2009 with a bunch of options that have all evolved out of the first argon ion to be used. So I think it's important to take a look at what's out there, what it does, what it doesn't do, and based on that, make some decisions about acquisition. So let's look at the anatomy of some of these sources. One of the first potential alternatives to laser light was to take a tungsten source and filter it to separate or isolate just that part of the spectrum that we were using to find fingerprints or excite chemistry. So if we look at tungsten, it's incandescent. So that means that you have a filament of tungsten wire, and you add electrical power to it, and because of the friction, when that runs through that little filament, it gets so hot that it incandesces or bursts into light. And you put some nice opaque stuff on the inside of the bulb, put in an inert gas, and you have your light bulb. So you have random emission, you got it going in all directions and all wavelengths of visible light. So if we take a look at it in terms of the spectrum, we find that even though tungsten is considered a white light, there are white lights and then there are white lights. And the thing that we are concerned with here in terms of finding something appropriate for the technique is more appropriately called color temperature. And that means the relative distribution of the wavelengths within that source. So those of you who worked in the old days with film knew that we had tungsten balanced film and daylight film because the two sources had radically different color temperatures, and if you used them inappropriately, you would get something that looked like it was bathed in blood, or you'd get something that was totally blue because the film was not matched to that color temperature of light. So if we look at the tungsten lamp, we find it has a little bit of blue, more green, just a ton of red, and then right off the scale in terms of infrared. So if you look at it, we want the light down in the blue-green region. You don't have to be Einstein to see that this is not the best choice. In fact, early on in about 1977 or 78, there was an attempt made to come up with an alternative by using two 1,000-watt tungsten bulbs, and you're talking about a lot of heat output there. Well, you can see the progression of that, and they had to use heat absorption filters as well as the excitation filter, and they ended up with 1/4 of a watt of useful power from two 1,000-watt bulbs. So that's not very efficient. So it has all wavelengths. It comes across as white light. But by use of filters, you could isolate one particular section of it. What happened, of course, with the development, and I would say the improvement of the alternative light sources, was that they came up with a bulb that was much richer in blue, a projection bulb, for initially one for a slide projector and then like a movie projector or for showing movies. And so the percentage went up. Now we come to laser, and this is a totally different thing. Laser stands for light amplification through stimulated emission of radiation, which is a mouthful. There was a Canadian comedian named Charlie Farquharson who called it a flashlight in heat. So the argon ion laser will detect untreated fingerprints through intrinsic fluorescence. Very expensive, at the time. That ours cost $25,000 in 70s dollars. Three-phase power. That big machine was 70 amps per phase, so you plug it in the city and there's a brownout. Water-cooled, very temperamental, eye hazard, exhibit hazard. Okay, it's true confessions time. Has anybody ever burned an exhibit with a light source? Oh, I know you're on camera and microphone, so we'll just nudge, wink, wink. But I'll confess, I was doing a green garbage bag on one occasion with the laser, and I looked and I saw what looked like a fingerprint, and I got a little closer, and oh, it's ridge detail, but it's a little bit faint. And I brought it a little closer, and it bubbled and it was gone. Anybody had that happen or heard of it happening? It's okay, you can nod. Don't. So it has a very, very serious exhibit hazard. And as I mentioned before, high maintenance. It's like owning a British sports car. You got to be a mechanic to really effectively own one. Not really portable, in spite of what we did with the mobile crime unit. It's transportable, but that's a different concept from portable. So how does it work? You have a gas tube. A vacuum has a critical amount of argon in it, and argon has an incomplete spectrum when you raise it to the point of incandescence. When you force the stimulated emission, it doesn't produce all wavelengths of light the way tungsten does. It only produces in the blue and the green. So you add, again, electrical energy to that, and you get the creation of light photons. And in this tube, you have mirrors at either end of that tube. The one on that side is virtually 100% reflection. Very, very high efficiency. They have to be cleaned. They have to be maintained, and that's where the instability part came in. And the other one is 12% transmission. And those mirrors have to be in perfect parallel this way and this way. And when they are, the light photons begin to oscillate back and forth down the length of the tube. And at this end, they're all being reflected, but at this end, 88% are being reflected and 12% are being transmitted through that mirrored surface. So again, it's not a terribly efficient production of light, and it's why, of course, it was three-phase power, why it was 50 amps per phase, why it was water-cooled, and why it was so temperamental. Because you had to have this whopping amount of energy going in, a lot of it being converted to heat, putting tremendous stress on all the optical components of your machine, all to get this little bit here. And all lines was, to all intents and purposes, composed of 488 and 514.5 nanometers. There were some lesser little lines in the blue and the violet, but and I think one more perhaps in the green, but very, very small percentage. So the pros of that machine: it was powerful. The beam was easily directed. You didn't have to worry about blocking anything because all of the output of that was forensically useful. And if you wanted to go with single line lasing, you could just simply change from your all lines mirror in the back and use any one of those lines you cared to. No wasted or interfering light produced. Big list of cons, big cons. Very expensive initial purchase, costly to run, three-phase power, water-cooled, and required expert maintenance. Our machine was breaking down a lot, and everybody knows when you do something for the first time, you never do it the best in your life. And there were a lot of things we didn't do well, and we learned painfully over the years. But our laser, first laser, was not the greatest piece of equipment in the world. We had a lot of issues with it. And the tragedy of that was that we were broken down almost as much as we were operational. And what was a equipment and supplier problem became transferred onto the technique. And people started to sneer and tune out. One of the most painful examples was early on, I would say about 1978, I got a call from the Georgia State Police, and there was a serial killer down there. And they just had another victim, and the stress was very high in the community, and they wanted us to bring our laser down and examine the victim. They'd heard about the fingerprints on skin and stuff. And I explained that it was not a portable technique. The laser simply couldn't be taken down. And he said, well, can we bring the body up? And I said, I don't know. Nobody ever asked me that before. So my boss and I went through our chief coroner for the province, and we got the green light to do. It was too late for this particular case, but we had an understanding that they had a plane waiting at the airport. They knew the guy would kill again. His cycle rate was increasing in frequency. And for the next victim, they were going to fly the victim up, and we had all of the green lights in place. I think it was a little easier to do in those days. Anyway, we got a call from the airport. They had their latest victim, and they were on their way, and I had to tell them our laser was broken. One of the worst days of my life. But that was one of the downsides of that technology. It was unpredictable, and you just never knew when you were going to be out of action. They had safety interlocks on it as far as the cooling went. If you didn't maintain a certain water flow, it would shut things down. And we found, for example, that our laser was breaking down every day at 10 o'clock and 12 o'clock. And what was happening is people were going to the washrooms at 10 o'clock, and they were flushing the toilets and running the water, and then they were running the water in the kitchen for lunch, and they were dropping the water pressure, the flow rate, and the laser shut off. So we ended up having to get a dedicated water line, and that problem ended. But this is, of course, how you find these things out. So it's not portable, and you still have this annoying coherent speckle, and yes, you can deal with it with that aquarium pump thing, but it's not the preferred choice. So if we look at those two options, and I say tungsten, but I realize now, in retrospect, that should probably just say a white light source. You have stimulated emission with the laser. You have incandescent emission on the other side. You have coherent emission versus incoherent or random emission, out of phase. You have straight line emission with the laser, and you have point source with the white light source. And of course, in that sense, the older photographers in the room will remember about the inverse square law, where the intensity of your light falls off in intensity as a function of distance. That doesn't happen in theory with the laser because the light does not diverge. So in theory, in a vacuum, the light is as strong at 5 miles as it is at 6 inches, which is why we can use a laser pointer to indicate. You can have a far, far more powerful tungsten source, and it simply won't do that. All it'll do is illuminate the whole screen. But that allows you to keep that light, even though it's just a little handheld battery thing, you keep that light together as powerful as it is at the source, virtually, to the point where it appears on the screen. Roland Menzel used to talk about his days in college where they would shine a green light on a brick wall from across the campus and move it, and people were wondering about this line and or spot on the wall, and could never figure out where it was coming from. Physicists. So the last characteristic is monochromatic versus all visible wavelengths. So then we come to the frequency doubled neodymium yttrium aluminum garnet laser, and that's the name of the crystal that's used to create that particular wavelength. And Roland used to say rather irreverently that you could laze carrot juice if you wanted to. But a great many things, depending on the material or the spectral properties, give you different output. So here we have, instead of a vacuum tube with argon in it, we have a pumped flash lamp and the laser rod, which is the yttrium aluminum garnet. So the output of this thing is the same with the parallel mirrors, and the output is at 1064 nanometers. But one of the interesting properties of all of the radiation from the electromagnetic spectrum is it all travels at the same speed, the speed of light as we call it, 186,000 miles per second. And an important equation in that is frequency times wavelength equal the speed of light. So if you double the frequency, you cut the wavelength in half. So you put a frequency doubler on the front of that device, and that drops the wavelength from 1064 to 532. So this is the configuration of the YAG. So what are the pros? Powerful, durable, portable, air-cooled, plug in the wall, and it produces only green light at 532. And there is no 531, there's no 533. That's very, very surgically, optically precise. So there's no wasted light produced, and this is a much easier job for a barrier filter to handle one wavelength rather than a whole band of wavelengths. So what are the cons? It's a pulse laser. The repetition rate got better, which that was annoying and distracting. But it's cool, cheaper to run, low voltage, and immune to vibration. Very long lasting. We had the development of the LEDs. And the LEDs are similar in technology to the semiconductor laser in that the light produced is a result of electrons moving in semiconductor material. And as a result of that, that can be engineered as well. So it opened up a whole new area in terms of developing light sources that were cool, robust, fairly cheap, and very, very long lasting. So we have a whole array of choices in the LED area, and they have some very definite advantages. The semiconductor laser is again similar technology, and the wavelength, as I said before, can be engineered. Now, since about 1980, the term ALS has been used, alternative light source, and I really take issue with whether or not that's a correct term. An alternative suggests or implies that you're going to get pretty much the same thing with this that you got with the first. But as I said before, if things are different, they're not the same. So this is the actual output of, that's the spectral output of the 505 filter, the polylight. And that is approximately the output of the 450, or the what they call the CS filter, the crime scene filter. Now there are differences between different manufacturers. Their filters are going to have different transmission properties, not going to be exactly the same, but they made the CS filter 1/3 the visible spectrum approximately to make it nice and bright. It's all blue light, but it goes pretty much from 400 to 500. So you look at that, and then you look at the 505, which is more selective, but there is the laser. These things are as different as chalk and cheese. So it would not be unreasonable to think that they would do different things. There is overlap. They do some of the same things, but there are things that the one does the other one doesn't do, and vice versa. One of my colleagues in Canada, a lady named Della Wilkinson, had this idea long before I did, and she felt that it was much more appropriate to refer to them as forensic light sources, and that way the sort of the mind thing about alternative would be kind of left out of it. So we're going to do some comparative things here to show the difference between the laser, and I just picked one of the sources to do. It got to be a little untenable to do all of them, but the results were pretty much the same, in fact indistinguishable, between the LED and the filtered lamp version, the polylight or the crime scope. So this was on white vinyl. Yeah, these are tough. Actually, in some cases, what you're going to see is basically little or no difference. But I think you can see there's a little better relationship between the background and the saliva in the laser. That's good, thanks. But again, we don't want to narrow our thinking. It's not only what we can cause the target to do, it's the difference between the target and whatever it's on. So we can accept less of a fluorescent response from our target if we're getting absolutely no response from the background. And the way I like to look at the whole process is that before we ever get involved in deciding whose fingerprint is on something, we are making the decision, we are reaching the conclusion based on our experience and expertise that that is a fingerprint, or that is a footwear impression, or that is a tire track. And so we are in the business of signal recognition. And once we recognize a signal, then it's our business to optimize signal-to-noise ratio by filters, by angle of light, by chemistry. So what's important is not the strength of the signal independently, it's signal-to-noise ratio. And that can change within the same source by changing to another color of goggles, or with the forensic light source by changing the filter. And if you were to take, instead of using the 450, for example, and hypothetically, because I can't remember, but if you were to use the 505 instead of the 450, the target item might not fluoresce as strongly as it did under the first one, but if you can drop out background interference, your signal-to-noise ratio becomes stronger. So these are important considerations. Semen. And one of the trends, I don't want to plant this in your mind, but one of the things you might see is that with the 450, you get a nice bright response, but sometimes you get a very bright response from the background as well. So sometimes it seems that there's a little better separation, even though the signal isn't as strong. And this is one where it really makes a difference. Untreated fingerprints. You should be able to see some ridge detail on the left and nothing on the right. And that is one of the difficulties with untreated prints that we develop through inherent fluorescence. Yeah.
Which laser is that? That's not coherent. Is that?
Yep.
Oh, it's coherent.
Yep. That's the coherent laser. Yep. Because aside from the things that fluoresce in our environment, like cosmetics and pigments and dyes that we may get on our hands, the stuff that we exude is not an in-your-face fluorescer. It doesn't jump out at you the way DFO or Rodeman 6G will. And I think a lot of stuff, with all due respect to everybody in this business, and including myself, I think we've missed stuff over the years because it is such a quiet fluorescence, because there is such a marginal difference between signal and noise, and we haven't always been on top of the situation, particularly when you got 75 or 100 exhibits and you're going through stuff. So as you can see here, just by dropping the lights, you were able to see that a little better, but it's never going to be one of those things that really screams at you. This is a little better example maybe. This is polylight. Can you see ridge detail on the left? Okay. And this is application of a narrow bandpass filter. Those are things that were examples of the laser outperforming or doing something that the light source didn't do. And here we have inherent fluorescence revealed by polylight. And this isn't meant to be an appropriate step. I just wanted to boost it up a bit so you could actually see the ridge detail. But these are all untreated fingerprints revealed by polylight. And this is an untreated print revealed by ultraviolet on the polylight with a yellow filter. Again, a little difficult to see here perhaps, but a lot of detail in that print. So let's take a look now at kind of the three categories here. And these are my findings, my impressions. But under the option of dollars, because the laser has shrunk in price, they have a smaller version of the laser we were just talking about at the last break. The prototype, or the one that first hit the market, was variously 6 and 8 watts. Very, very powerful. My personal opinion is you don't need that much power. The compact one they have now is 3 watts, and the only difference in terms of reach is 1 full photographic stop, because I did a series of comparison photographs at 6 and 3 watts, and it's very difficult to see much of a difference. Is it possible that something could be just on the threshold of your ability to discern, and you might get it with one and not with the other? Yeah, but I don't see it as a huge issue, not one that necessarily would lead me to suggest that you absolutely need that big one. Body fluids. They all work very well for body fluids. Rodeman 6G. Again, they all work really well for Rodeman 6G. Brilliant yellow, coming back to what Ken was saying earlier. You're going to get much better results with the filtered lamp or the LED, because you have the option of hitting the brilliant yellow where it lives. It loves blue light. And you can do better with this little LED at 450 with brilliant yellow than you can with that powerful big laser, because it's in the wrong spot for that chemical. It doesn't have a good absorption in the green, but it has a wonderful absorption in the blue. DFO, and they're all performing very well in DFO. And again, the same thing with indane dione. Now we come to the other area. Untreated prints, in my personal finding. But again, as I said before, there are occasions, there have been occasions, and all of these, I must tell you, all of the ones have come to my attention in about the last 5 years. Prior to that, I was not aware of any untreated fingerprints responding to light source. There's been anecdotal exchange between colleagues for the last 3 decades that have told us that lasers are more surgically precise in terms of isolating very, very quiet, untreated fingerprint fluorescence. But it really hasn't been kind of tabulated or brought together in any kind of way that I'm aware of. And in terms of portability, you got to give the nod to the LEDs. They work really, really well for that. In terms of photography, again, there's not a lot to choose here. The LEDs are very powerful. In fact, it amazes me that for something that small, these handheld sources, and you've got the crime light, you've got the Flare Plus, which we have here to look at, but they're all generically very impressive. And then the ultralight, which I call a bent one. Anybody have one of those or have seen it in operation? Yeah, they all work. They all do a good job. Ease of use. And I give a slight nod to the LEDs again, simply because they're small. You can position them easily and move them around, and it's not quite so easy to do the others. And we're going to have first-hand experience of that this afternoon when we start in by looking at the samples. Reliability. I think they're all kind of at their operational optimum now. They've ironed a lot of the bugs out of every one of those to the point, and somebody may take issue with me if you've had a serious problem with your light source and had it out of action for extended periods of time, but I have not had that experience. So all of the choices offer clean, uniform light because the laser, the new semiconductor laser, has solved internally that problem of coherent speckle. All choices work very well with the chemistry we have, with notable exceptions. As I said before, you're not going to have the laser working really well with either brilliant yellow or acid yellow if you're doing blood impression enhancement, because you have more choices. It's like having a box of crayons with 30 colors as opposed to one really nice color. Lasers are the most sensitive, in my experience, for untreated prints. Fibers can be revealed differently by the different light sources, which, in my opinion, is why it's a great idea to have that range of excitation choices, particularly for crime scene stuff. And as I said before, it's the difference between the target and the substrate that's key. And you can accomplish that either by changing your light source, that is the excitation, from one band to another band or to monochromatic, or you can change by your barrier filter, or combinations of the two. Lamps and LEDs are more versatile and lighter. All choices now work pretty well on location and in the lab. And all of the choices require some sort of clamp for photography. You need something, a Bogan clamp, or if your light source has a tripod mount or something of that nature. And of course, one of the big advantages is that the laser in the 6 or 8 watt model will operate on battery, and you can quite literally be out in the middle of a farmer's field working for 2 hours. That's 2 continuous hours of examination time just on the battery at full power, which I think is pretty cool. And LEDs, of course, they have a very low recharge period. The batteries are getting so good that the recharge period is shorter than the operational period, so you can actually have your one battery charging while you're using the other one, and it's going to be ready long before you run out of power with the one you're using. I'm going to borrow a phrase here from Al Gore, inconvenient truth. Our business is loaded with inconvenient truths. This stuff is messy, complicated, frustrating, and it doesn't have one magic pill, one magic answer. There are too many things involved. Lasers are monochromatic, lamps and LEDs are broadband. They do many of the same tasks, but they don't do exactly the same things. Each has the ability to find things the other one misses. If we don't use both, we may be missing evidence. That's an inevitable conclusion that I have come to. And that is a big inconvenient truth, because everybody is trying to do the most with what they have. We, in our business, are certainly dollar dependent, but we're not dollar driven. We're not out to save the government money. That was never our mission statement or our mandate. And you don't say, in response to bean counting, that if we decide to cut off our hands and feet, we're going to save the government a ton of money on shoes and socks and gloves. Because if we do buy into that kind of philosophy, we end up paying way more to reattach the hands and feet down the road. We are event driven. And that's one thing that I always liked about working for a police department. In spite of the bureaucratic issues that we've all had, the constipation of working within a huge infrastructure, the one thing I liked about government work in a police force was the clarity. I knew why I was there. I knew what my job was. So we have to get the right techniques for the right reasons, bearing in mind that we are dollar dependent. But given that we know that certain things have a level of urgency, I always felt it was our responsibility to make sure that the higher-ups knew that, and at least they may not buy into it, or they may not buy what we want, but at least they would be making an informed decision. The right equipment for the right reasons, the right techniques for the right reasons, and that's true economy, doing it right for the first time, or doing it right the first time. So, any questions? Comments on experiences? Yeah.
Do you know of any specific research that shows how many prints are missed, or that are developed with inherent fluorescence and then not developed later?
That's a tragedy that kind of work has not been done. Like we've had 30 years of fluorescence examination, and to a degree it's kind of been reactive. We pursue a particular line of research and we drop things. You'll find that things get dropped in the stage of evolution, and then they get returned to, like the YAG laser got returned to 20 years after the fact, or no, not that long, 10 or 12 years after the fact, because its time had not come. But to my knowledge, there was no formal quantitative study done between what was available through untreated detection versus with lasers versus forensic light sources. Everything that I saw on the subject till about 5 years ago was totally anecdotal. You know, you'd say, well, I found something with a laser, I didn't see it with a light source, and the other person would smile and nod their head. Very difficult to quantify, as I say, because it hadn't been done before. Now, it's not to say that anyone is in this room or outside the room, for that matter, is going to have exactly the same experiences that I had, but I think the trends are there. I think that, and I'm not recommending one over the other. I'm saying that they are complementary rather than, yeah.
Why these companies don't work together to get one?
That's a good question. That goes outside my realm. I'm a lousy salesman. I'm more in the lab kind of person, and but when you come to it, that brings up a very important point, because those people are dollar driven, and rightfully so. Leslie asked during the break if there was any development towards a laser that would give you like a tunable monochromatic output, so that you just twist the button and you go from a 460 single line to a 505 single line to a 575 single line. And one of the short answers to that is there hasn't been enough critical mass to drive that, because companies don't want to spend a ton of money they don't know for sure they're going to get back. That would be, I would think, an excellent government funded project. And once the feasibility, or as we might say, once the market is shown to be there, then companies will go in and say, yeah, it's worth our while to do that. But it's very difficult in the first go to do that. And of course, they don't talk to each other because they're all trying to sell us stuff.
Because in history I am seeing the same again and again and again. We have the sample of fingerprints, the Bucetich system in the Spanish community, and then the Henry system in the English community, and they never get together. So they made the same mistake. And also the AFI system, Logica in England, Morphos again in France, Motorola, Pintrack in the United States, Cogent, but they never get together. If they get together, probably they will get a better product for everybody. But I don't know why they don't work together. That's my big question.
Well, I guess we live in a kind of a cloistered community where we are, and I think, privileged to be event-driven. Because outside of that, everything is dollar-driven. Everything is driven by economics. And I think that's what held back development on a lot of the things that we had. They had to see there was a market there that would justify doing it. And that will be true of anything we do, really. So probably the best approach to that is for us to do the research we can to bring to the corporate sector the truths that we find, and then they can make their economic decisions based on that. And that's not a pejorative when I say they're dollar driven. They should be. They have to be. Otherwise, we wouldn't have anything. But it's very different from we don't have the same agenda. Our agenda is to solve crime, and you don't always. It's expecting a lot for a company to invest a lot of money in something that they don't know they're going to get some kind of return on.
With fingerprint residue on skin, you're saying that 505 is the best light to use on that with your testing that you've done. Now, is the reason the laser working better than an ALS is because the ALS is not specific at 505. It's got the range, say, from 485 to 515, and the laser's just boom, 505, and that's what's making it light up?
No, not what I said. On skin, untreated, I'm not aware of any findings other than that first one with the visitor to our lab, and that was 514.5. That was the Argon laser. We didn't have any other light source to compare it to at the time, so I have no idea what that might have involved. Skin is a whole different ball game right now. But it brings up an interesting point. There was a very good research project done at the RCMP Field Ident Resource Section, I'm guessing at about 10 years ago, where they were using something called tech dye. And tech dye is phenoyl europium chelate, which is a rare earth dye. And it has a fantastic and very interesting quality. Now, this technique didn't work operationally, and it's been shelved or deferred, but I would try to keep the name in your mind. And the reason is it exhibits fluorescence in the deep red, but it is excited by ultraviolet. So it's got a huge Stokes shift. So if you were to have a filter which just cut off on the outer edge of the fluorescence, so a filter that essentially blocks all the blue and green and yellow and only transmits the red, you're going to have almost no chance of any background fluorescence. And in fact, the images that they produced were very, very devoid of any background fluorescence, just black matrix. And of course, that's really important with any kind of fluorescence technique on skin because skin fluoresces. And so this was a technique of superglue follow-up with the tech dye. And as I say, it was abandoned. But I have a hunch that europium may surface again in some other version or some other way, just because those fluorescent properties are incredible. Okay, I think that's it.